Hello.
Yes, Professor.
This
Yes.
call is now being recorded.
So let's start from here, right?
Yeah.
Because I finished here and started taking your question, right? Okay. So, yep. Are you with me?
Yes, sir. Yes, sir. Yes, sir. With you
Okay.
only. Yeah.
So, what I'm going to do is now I'm going to talk about some of the research we are doing at Robert Gordon University on solid oxide electrolyzer development. This is our team. Two university working on. One is Robert Gordon University, as I said, Professor Nadimul Faisal and Professor Mamdud Hussain, that me, and my colleague Dr. Anil Prathuro is a lecturer in the team. We have two researchers, Victoria Kurusina and Vinod Rajendran. Dr. Victoria Kurusina is a postdoctoral researcher and Vinod is a PhD student. So this is our team here on the top. You can see uh, the figure here, and this is the team from our partner university, University of Surrey. We have Professor Dr. Bahaman Hori and Professor Kiang Kai and as the lead, and Ajit Suman as the researcher here. And this project is funded by UKRI and also uh, ICISIS Neutron and Muon Source, National Nuclear Laboratory, and things like that. Moving on, uh, the temperature effect that I wanted to talk about is here. If you want to produce uh, hydrogen in electrolysis, you have quite a number of options. You can have low temperature, liquid hydrogen. Uh, you can use liquid water to produce hydrogen below 100 degrees Celsius at a PEM fuel cell. If you want to produce hydrogen at a very high temperature, this is the advantage. Your high temperature, your total energy demand, of course, goes up. Higher the temperature, higher the energy input you need. However, the type of energy changes. That means at high temperature, you need less electrical energy and more heat energy. Obviously, heat energy cost is less than electrical energy. So that is the advantage of producing hydrogen at very high temperature. You need less electricity, more heat. For example, where is the heat coming from? Heat can come from geothermal source. So if you dig into up to 1000 meter, 3000 meter, or 5000 meter, you can get a temperature of 440 degrees Celsius, 90 degrees Celsius, and 150 degrees Celsius. This is not enough, but you can increase that using a heat pump to higher temperature. However, there are a lot of waste heat at very, very high temperature in UK. And if you look at electricity generation, that produce about 390 terawatt hour of electricity. When we are producing electricity, these are the amount of waste heat that is generated. In Aberdeen, where we are, there is a actually large amount of maximum amount of waste heat available here in this area. Heat is cheaper than electricity, so if you can use waste heat, is even cheaper. However, it's very difficult to hold and store. So you have to use it somehow. You cannot store it or hold it. That's the challenge. Another options. Can you still with me? Are you with me? Hello.
Yes, yes, Professor.
Okay. So because I am mindful of, oh, can I use this type of slide so I can keep an eye on my screen also?
Yeah,
Internet
it's fine. It's
instead,
fine, sir. It's fine. It's fine.
instead of full screen. Okay.
Yeah.
Okay. So in this case, if you moving on to nuclear energy in UK, there are a lot of uh, few nuclear energy sites is there. Two are in Scotland, here in Tornes and in Hunterstone. What is the advantage of nuclear? Is that 60% of heat is wasted in nuclear plant. So if you can use that nuclear heat, then we can substantially produce hydrogen without uh, applying lot of new energy. So using waste heat is a lucrative way of producing hydrogen. Now, if you look at how the nuclear system work, this is probably a module, and you get a steam coming out from nuclear plant, and it goes into a uh, turbine, steam turbine, and it's run it here, and you produce electricity. So we can have a bleed line from this steam, and then it can goes into a steam electrolyzer. For the time being, the idea is not to use the steam directly into electrolyzer, but rather use through a heat exchanger to transfer heat from this steam in uh, nuclear plant into electrolyzer. And these are some numbers to quote in terms of understanding how we can produce hydrogen from electrolysis. Uh, the UK target is to produce 10 gigawatt of low carbon hydrogen by 2030. And if you look at renewable energy, 75 gigawatt of renewable power should be connected to the grid to achieve net zero target in UK. Ambition of nuclear sector, that the nuclear sector we showed you, is to produce 75 terawatt hour of hydrogen by 2030 from steam. And in that case, high temperature electrolyzer, solid oxide electrolyzer is at the forefront of using this nuclear heat into hydrogen production. This true technology is very matured, but solid oxide electrolyzer runs at a high temperature. It can use waste heat. So that's the advantage. As I said before, in UK you have nearly 391 terawatt hour of waste heat. If you can use that, it will be a lot of advantage. Currently, hydrogen production cost from nuclear power and waste heat is about 2.79 uh, pound to 5.74 pound per kg. But in future, our estimate or NLL estimate, that is nuclear National Nuclear Lab. This is our partner. We work with National Nuclear Lab, and their forecast is to reduce price to 1.24 pound to 2.14 pound per kg of hydrogen production. Okay, so that's our research work. What we have in solid oxide electrolyzer. I will explain the science little bit now. So if you look at this is a figure here on the left, what you have is a tubular structure. In the tubular structure, in this tubular structure, we usually have three layers. One is this green part, which is what we call cathode. Then there is a white part, which is anode, and then black and white part here is called anode. Sorry, cathode, electrolyte, anode. So three layer: cathode, electrolyte, anode. And this is then connected with a outer power supply. We take electron from anode and supply the electron into cathode. So inside this tube, we have steam at a high temperature flowing through this tube. That steam is split into hydrogen and oxygen. What happens is that we apply electron into that steam, which split this is this atom. So we ended up with electron going into oxygen and is turning into oxygen ion, oxygen minus 2. It's taking 2 electron from this circuit. And hydrogen combined together producing hydrogen gas. So we have a hydrogen gas in cathode as well as steam. So what happens to this oxygen ion? It flows through this electrolyte. So electrolyte is a type of material which is ion conductive. It only allow ion to flow through this electrolyte, and then it goes into the anode section. In the anode section, oxygen give up this electron and become oxygen gas, and then electron then flows through anode into the cathode again. So in this structure, we are splitting water into hydrogen and oxygen. oxygen in the form of ion. That ion flows through electrolyte into the anode section. In anode, it gives up its electron and become oxygen gas, and then electron flows through anode into cathode again. This is the whole system. Is that clear? So, in that system, we have developed our own expertise is to add a structure. So, what structure we put in? We put in a tube as a support, because previously when we have a cathode electrolyte anode system, you have to make this anode thicker or is cathode thicker to support the whole structure. So it's called anode supported, or if you make this cathode thicker, you have a cathode supported. The problem with this thickness is that then you include lot of electrical resistance into the system. We are trying to reduce electrical resistance. In order to reduce electrical resistance, you have to make this structure thinner. If you make it thin, it's electrochemically very good. You can have a better efficiency, but you don't have the stability of the structure. So what we have introduced is a support tube. We call it porous substrate made of stainless steel, and on top of that stainless steel, then we put a layer of uh, cathode electrolyte anode. In that cathode section, we have putting two different type of metal. We are putting nickel oxide YSZ and nickel oxide GDC. In electrolyte, again we split the electrolyte in two different material. Is a YSZ is a common material. Then we put GDC also. So some of this material is better in ion conductivity and gives you lower price. Then GDC is cheaper than YSZ kind of thing. And in the anode section, we have GDC and LSCF. Not only that, in the anode section, we have also treated the surface with this type of meta structure. And we hope that meta structure will give you more area and more area for electrochemistry and more area for oxygen to flow, and that give you better efficiency. So from the standard design, we come up with a quite a innovative design based on a tubular support and restructuring this cathode electrolyte and anode layer into different multiple layer with multiple porosity adjustment and also thickness arrangement. And with objective is to make this very thin compared to substrate, so we can have less electrical resistance into the system. Okay, now these are some of the material we used in our production. This is a slurry of nickel oxide with GDC. This is a slurry of nickel with YSZ. This is YSZ material. This is GDC material. This is LSCF GDC material and things like that. What we did, look at powder form before we creating slurry to look at different type of microstructure, and we can see YSZ have a very spherical structure, and silver had another structure, and nickel oxide has different structure and things like that. Now the fabrication process, we took a stainless steel tube first of all, then we did electrodeposition of silver on the tube. We use two different tube. One is solid oxide stainless steel, one is titanium tube. On top of that, then we coated a deep coating. Hello, deep coating of we applied a deep coating of we applied a deep coating of uh, different cathode electrolyte and anode layer on top of each other. We have done it using dip coating. So if you look at this side here, we are just dipping it by hand, and then we sintered it for a long time, and we have to do a high temperature sintering. Okay, so at the end, we ended up with this type of structure on a tube. We have a exposed cathode here, electrolyte, anode. Black part is anode. This gray part is kind of electrolyte, and white is a part here is our electrolyte, and sorry, is cathode. So three layer here. And then we took the tube. We also did another method of spraying, which is called thermal spread of anode and cathode layer deposition. So we did it by manually, by hand in our lab here, which is deep coating. A very simple technique. We just coat it, take it out, did it high temperature sintering there, and then we also in some other tube we have this type of thermal coating layer put on this tube. So we ended up with a tube, something like that. So stage by stage, we took a stainless steel tube. First of all, we coated silver, then nickel YSZ here, then nickel YSZ, YSZ, and GDC, and finally LSCF YSZ coating. So we have a the exposed area here, anode, electrolyte, cathode. So on that tube, we now need to put electrical connection. Now we pass some DC voltage. So one end is both end is exposed. We have the cathode area exposed. We connected with a wire, and this surface is anode. We connected with the wire. Then we did little bit of characterization. We look at ACM graph and look at how these layers are deposited. If you look at the cathode layer, which is average 112 micron, we have an electrolyte of 8 micron and anode of 49 micron. Cathode layer, we actually wanted to have very thin cathode layer, maybe 40 micron and things like that. But we ended up with 112 micron. So we have to optimize the system to uh, get it better system. And then we did some experiment. To do the experiment, we have the water tank, we have a metering pump, then it goes into a control evaporator and mixture here. We evaporate water into vapor. We also get hydrogen and uh, carrier gas into the system, because if you don't mix hydrogen with steam, that tube will be corroded very easily. Then we put the whole system into furnace with the heating element. Once we heat up to desired temperature, we put it through the tube, and steam and hydrogen produced through the tube. It comes down here and into a cooler coil heat exchanger, which is condensing coil. We condense the water out, and we take the hydrogen into a syringe and store it here and do some experiment to see what is the purity of hydrogen. So this is our experimental setup, and this is our output. If you look at output, how you measure the performance of electrolyzer, it is measured with this type of voltage current graph. In a voltage current graph, what you have is for a given voltage, say 1.4 volt, the more you go, more you have current density, more hydrogen you can produce. So for a given voltage, if you have a higher current density, that means it's a better system. So in our system, we achieved a current density of 3.7 amp per centimeter square at 1.2 volt at 400 degrees Celsius. So that's a very good achievement compared to what is in journal article. Most of the journal article shows that you get a current density about 1.5. So we achieved 3.7. This is a massive achievement compared to what is there in the market or what is there in the research lab. Why you achieve that? Because we have a very strong support. We managed to thin out cathode, electrolyte, anode. We have adjusted their porosity gradually, and we have multiple layers. On top of that, we have a microstructure on the anode surface, what we call meta surface, and that surface also create better oxygen electrochemistry and movement of oxygen away from the surface. So we are very pleased with our achievement, experimental achievement here. On top of that, we did a lot of CFD modeling to optimize this type of microstructure. So this is the structure of a CFD model. We have steam inlet coming through the tube. We have the substrate here, and then we have cathode electrolyte anode here, and the air uh, flow here. And on that, we develop, this gives you the mesh characteristic, and we have to of course compare our CFD model with experimental data or previous calculation, and we have verified our CFD model with previous experiment of Slatey and Hagiwara data, and we are confident that our model is correct. Once we have got this model, we have adjusted the surface on the anode using different type of meta surface like small square, parallel line, net square, and twice large square, and things like that. So this is the meta surface we have used in our uh, CFD modeling for different type of meta surface. And at the end, we have found out that meta surface actually improve the performance. So this blue line here is no plane surface, and these are all for meta surface. And one of the meta surface, which is the square net pattern, I think this one produces the highest performance. How do you know that? Because again, in order to improve this current voltage curve, you have to look at a fixed voltage, and you have to look at, for a given voltage, which gives you the highest current density, which parameter gives you the highest current density. So you can say that this net structured surface give you the highest current density. So that means that is the base structure, and we have manufactured those structure and come up with our experimental setup that gives you the uh, performance that I showed you. Not only that, we also looked at thermal stress onto the system. So we have simplified our simulation. We have this stainless steel substrate. On top of that, we have different layer of cathode electrolyte anode and two interconnector to carry electron from anode to cathode. And we have looked at thermal stress onto the system. So we have looked at stress at 600 degrees Celsius, and we can see in this type of structure, hoop stress is usually the highest stress, and you can see the hoop stress on the outer layer is very high. If you look at longitudinal stress, also at the end, you can see stress along the tube. So when you are holding our tube, if you look at our tube here, we have got two screw connection to end. Actually, we have two screw connection with two end, but when we are doing our experiment here, we don't we here we don't fix both end. We have to keep one end free and one end screened, so there is space for thermal expansion. Another problem we have is that we have different type of material for cathode electrolyte and anode, and this doesn't have the same thermal expansion coefficient. If you don't have the same thermal expansion coefficient, that will expand at different rate and can produce different type of thermal stress, and that we observed in our modeling here. If you look at the sixth layer, which is outer layer, that is subjected to a lot of deformation. So if you look at this color here is red, that is deformed under thermal stress. Fifth and sixth layer has got a lot of deformation, where the inner layer doesn't have that much of deformation. So in our experiment, we also observed, after running this tube for hydrogen production, we have noticed that there is a lot of crack on the outer surface, and we can see from our modeling also it is subjected to uh, deformation, and of course it can subject to crack, because the three different material we put it on top of each other, they don't have the same thermal expansion coefficient. That's a challenge to find material having the electrochemical property as well as thermal property. So at the end, what you can say is that we have developed a new electrolyzer design that actually performed really well compared to what is there in the literature. Also, we have used surface structure modification, putting metasurface, and that also improve the performance by 10%, roughly 8.58%. And if you look at high temperature process, we have seen this material is still debonding and cracking, and that is observed both in experiment and in uh, finite element modeling. We can see there is a lot of deformation happening and cracking happening on the surface. Another research project we have been doing is trying to optimize solid oxide electrolyzer performance. This is one of my PhD student, Safayawati Hasbi. She is just been working roughly 1 year and things like that. This is the planar electrolyzer, again solid oxide electrolyzer. So we have two channel, one for steam flow and one for gas flow, air flow, and then we have the structure here of cathode electrolyte and anode, cathode electrolyte and anode. And this type of planar cell, again, we use the CFD modeling or computational fluid dynamics modeling to look at the performance. First of all, we have compared our results against experiment of previous published data, and we have seen that our CFD modeling matches reasonably well with the published data. That means we are confident that our CFD modeling results are accurate. Then we move on to do some sorts of parametric study. We can run this electrolyzer at different voltage. There is a term called thermoneutral voltage, below which you don't need to put additional heat, because whatever heat is generated during the electrochemistry, that's good enough to maintain high temperature. And if you increase the voltage above thermal neutral point, you have to put in heat, extra heat, to run the system. Okay, so originally you may think it's better to run below thermal neutral point at a lower voltage, but in practice, if you see this, the performance of the hydrogen production rate versus voltage, you can see increasing the voltage give you higher hydrogen production rate because it produces higher uh, current density. So even if you put a little bit of heat into the system, and if you get this heat free from waste heat, then that's not a problem. You should run your electrolyzer above thermoneutral point. That gives you higher hydrogen production rate. If you look at the temperature again, higher the temperature, higher the hydrogen production rate. It is quite obvious at high temperature you have higher electrochemistry. Uh, uh, that means you have uh, higher activation potential, uh, better electrochemical reaction and things like that at higher temperature. So you get higher hydrogen production rate. However, at high temperature, you have the problem of debonding and cracking. So it's not always possible to run your electrolyzer at very high temperature. That we have the material limit and things like that. From the uh, performance point of view, it's better to use at high temperature. And also, if I told you that if it in your steam channel, you have to mix it with hydrogen, otherwise you have corrosion on the electrolyte. Uh, to begin with, and electrode to begin with. So how much hydrogen you need to mix? If you use 50%, or you can do 90%, and you can see that more the steam you have, more hydrogen production rate is. So better if you have 10% hydrogen and 90% steam going into your system, you get the better uh, output, especially at high temperature. But low temperature is not much difference in terms of proportion. And if you look at this trajectory, it's not that high either. So you need to have certain amount of hydrogen mixed with steam to go into your cathode channel to initiate your electrochemical reaction. Okay, another project we have been doing is to look at hydrogen blending into the pipeline. So the idea is that you have a main transmission line here, and in that main transmission line, you want to blend hydrogen so that when it goes into your end user, especially in UK, end user is in your house where you are either cooking food or heating your house using a boiler. So in UK, you have natural gas coming into your home. You have a boiler there, and that boiler then uh, combust, create heat. It heats up water, and that hot water or heated water then circulated through the building to keep your room heated. So that's the major use of natural gas in UK in terms of keeping your building hot. So in a transmission line, you can mix hydrogen and blend hydrogen, and without changing your boiler, without changing your uh, cooker, you can blend up to uh, 5 20% of hydrogen into the natural pipeline, existing pipeline. However, in Britain, the health and safety executive that have given permission to mix up to 2% only. 2% of hydrogen you can blend it now, and they reckon is safe to blend 2% of hydrogen rather than 20%. To go into 20%, you have to do a lot of research and show them that it is safe. For example, they have given permission for 2% mixing, and this is a safety simulation where we have a mixing using a T junction here. So you have methane coming in from left to right, and then you are pumping hydrogen to mix it here, so that the blending ratio will be 20% hydrogen, 80% oxygen. uh, okay, 20% and 80% by mass. So this is the blending ratio uh, we are looking at. But what happened during the mixing process, we can find it from CFD modeling. Number one is your velocity is low here coming in for methane, and we are putting hydrogen at a higher velocity. If you mix it here, velocity goes up in this zone here, and then it drops again. So this is a critical location, and then velocity remain almost constant along the pipeline while the mixing happening. Velocity is not interesting, but if you look at the pressure profile here, you can see the pressure was high in the methane stream, but once you mix methane with hydrogen, pressure drops significantly, and then pressure remain low here. The Now you have to balance your compressor and compressor station based on this low pressure pipe system. Where you have a high pressure for methane, you have now low pressure after blending 20% of hydrogen, 20% of hydrogen into the system. So you have to think about your compressor and the distance between different compression station and things like that. Another challenge is happening in this mixing is that though we are saying that we have 20% blended here and pipeline is safe, but if you look at hydrogen uh, percent during blending, at the top of the pipe, hydrogen portion goes up to 1%, nearly 1% during this mixing point here. Then it gradually drops towards its average value of zero point 0.2. If you look along the center line, it also from 20%, it jumps up. No, initially it was zero because there is no hydrogen here, only methane. It jumps up to about 20% or more than 20%. Then it slowly drops and then stays a uniform location. So that section of the pipe, top part of the pipe here, is actually 100% hydrogen. And our health and safety executive, they are not really worried about this mixing process here because up to 15 to 20 meter long of the pipe, hydrogen proportion is a lot higher than they have certified. They have certified only 2% of hydrogen blend, but in some or even 20% hydrogen blend, but in certain location during the mixing, you have a 100% of hydrogen before it completely mix, and this length is about 20 meter. So we have to come up with a better mixer design, so it mix up really quickly into 20%. Number one. Number two, if you look at this pressure profile, pressure actually drops significantly compared to methane pressure, and this drop further down, this pressure will drop linearly because of the friction. And there is a worry that when the pressure drops significantly, there is a chance of stratification of gases again. There is a chance that chance that methane and hydrogen will separate out further down the line when the pressure is low, because there is a massive density difference between these two components. Okay, so that's the type of research we are doing on hydrogen in our university. So that's we came to the end of my presentation. Hopefully, you managed to listen to it. Now, I'm sorry that I was cut off, but I will be happy to take any question that you have. Thank you very much for your attention.
Thank you, Professor Mahmood Uzain, for your valuable talk, valuable insight, and the research which is happening at your university. So almost 150 it was there. Now they in 126 participants there in call. So they will be might be taking care of what you call it in your insight in the research work, or they may be for an further academic research. So if any participants, if you have any further questions, please you can have a questions with Professor. Yes. Over to participants. Dr. Tiba Pandri, you can ask questions in the live.
Okay, for hydrogen generation, we used ANSYS Fluent. For the CFD modeling, we used ANSYS Fluent. They have a uh, add one module for electrolysis.
Okay, sir. And you can use the MATLAB. Anything related to MATLAB is having any library for the simulation purpose.
Yes, we have written our MATLAB code. Those are one-dimensional code. So we are just looking at uh, performance characteristic. That means what is the impact of temperature, what is the impact of pressure, what is the impact of maybe porosity also we can include. Mm, but we cannot look at the whole distribution within the electrolyzer itself. So if you can think electrolyzer as a box, and then you have input and output, then we can do that using MATLAB, one-dimensional analysis.
Okay. Okay,
Yeah,
sir. Thank you, sir.
we have written code for that also, and Python also. Another current trend is to use Python to write computer program. Yeah.
So there is any the use of AI for the hydrogen generation techniques.
Yes, if you want to do optimization, if you want to
Okay.
do uh, like a modeling in terms of what you call surrogate model and things like that, if you want to develop, because a lot of the characteristic curve that we have generated from experiment we can feed into AI model, machine learning algorithm.
Okay. Okay, sir. Thank you.
And that's the active research area also.
Yes, sir. Yes, sir.
Any other participants? If no questions, then we close this session. Then we will join for an in valedictory at 6:30, where our Professor Mahmood Hussain also will be joining us guest of honor. He accepted our invitation and be joining there at 6:30 to 6:30 to 7. It will be valedictory will be over.
Yes, after 1 hour, right?
No, so one we have 1 hour time, so they
1 hour.
can. Yeah,
Yeah,
it's
in the same link, right?
same links, same
Okay.
links.
So again, please accept my apology because my internet cut off, which I didn't realize in the middle. Number two, thank you very much for your attention. You stayed patiently while I was cut off, and I didn't actually realize. So I continued my talk and finished it.
Okay, okay. Oh,
Only then I realized I was cut off. And the final point I want to make is that I am keen to collaborate with anybody working on this area. So I have quite a number of partners in India, especially IIT Dhanbad, VIT Vellore, and uh, Motilal Nehru National Institute of Technology, I think NIT in Allahabad. So
Oh, that's very nice.
I will be keen to collaborate with you. If you're interested, you can email me. That's the best way to contact me, or through LinkedIn also. You can contact me. I'll be more than happy to collaborate. Thank you very much.
Thank you, Dr. Professor Mahmood Hussain. So it's very your kindness
Sir,
and
please share your
email.
email ID, sir.
Yeah, I can do it now. If we can find out the chat, right? Okay, here it is.
Put it in the chat box so people can understand. So otherwise,
Yeah, is there? Okay, is you will find it in the top, I think.
sir, properly shared in the chat box. Please, you can
Yeah,
have full details.
yeah, sure. Thank you. So we'll come back after 1 hour, right?
Yes, sir. Yes, 6:30
Okay.
you can join. So there is a chief guest is Professor Dr. Velraj. He was a immediate past former vice chancellor of Anna University. Sir
Oh,
also active researcher on thermal energy storage, thermal things. Probably it will be good address to all the participants. And also you can also have an interaction with him, sir.
okay, great. Thank you. See you soon then. Thank you.
Thank you, thank you. So we'll join at 6:30, sir.
Okay,
Yeah,
Sir, I
thank
have
you,
one more
sir.
question.
sure.
Arun, please.
Sir, can you please tell me the durability of solid electrolyzer which is used in solid oxide electrolyzer? Means,
Durability, right?
yes, sir.
Durability is low. I have seen, I have shown in your my presentation is that after we used it for even for few hours, it actually cracked. Okay,
You
so
have
we
shown
need
some materials, sir. In that, which one is best? Which means why is yttrium stabilizer zirconia, some
so
and then something.
the anode structure with LSCM and GDC that
Ah,
delaminated and cracked. Okay, outer layer. And if you look at our finite element modeling, it also shows the outer layer is the one where you have lot of deformation and stress, hoop stress.
oh,
That okay. Okay, so its durability is still very low. You really need to do a lot of research in that area, especially the production process, because we did it manually with just a deep coating and sintering. So maybe we need to have better manufacturing method to make it more stable. I don't know, to be honest.
okay, okay, okay. Thank you, sir.
Okay. We need further research.
Okay,
That
okay, fine. Okay, thank you, sir.
yeah. Thank you. Okay.
Okay, Professor. Okay.
See you soon. Then.
So we'll join at 6:30, sir, please. Thank you. So all the participants, you stay connected and be with us at 6:20. Probably we'll start at 6:30 as per the schedule our valedictory functions. Now it's a tea break.
Okay, can I stop the recording, sir?
Please, 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 please. We
Okay,
start at 6:20. Okay?
okay,
All
okay,
right.
sir. Right, sir.
Okay.